Hi, my name is Reuth Mirsky. I'm an assistant professor in the computer science department at Tufts University. This is my new faculty highlights talk for AAAI called Bad AI, Good AI, Rethinking the Agency of Our Artificial Teammates. Ever since the term artificial intelligence was coined, there have been debates about what it means to create good AI agents. These discussions traditionally highlight the importance of safety, and recent work have refined this notion and claimed that a good AI agent should also be one that can understand what we want from it, and on the other hand, can act in ways that we will understand. It should also be aware of its own resources and use them efficiently. A very important assumption that these works make is that a good AI agent will be compliant and will also act or try to act as it was instructed under the safety constraints it was given. In my research, I argue that compliance is not always desired. For this, I take inspiration from guide dogs. These are dogs that are trained to lead blind and visually impaired people around obstacles. They're unique in being the only service dog that is not just trained on obeying its owner, but also on intelligent disobedience. If they are given an unsafe cue from their handler, they are taught to disobey it. So, for example, if the person wishes to cross a busy street, but a car is approaching fast, the robot knows to disobey even if the person insists on crossing. This understanding makes the dog a very intelligent collaborator. The dog usually does obey, and now needs to understand both a context and a state that are so unsafe that it should not obey its owner or even force action on them. So in my research, I'm interested in these types of questions. Can we design and build AIs and robots with intelligent disobedience? And can we design a guide robot that can intelligently disobey? Consider a visually impaired person that uses a guide robot. In this talk, I'm going to cover the answers to the very important question, why didn't the robot cross the road? So first, an important global objective in this situation is the safety of the handler itself, obviously not getting hit by passing cars. However, the handler also has a set of local objectives in this scenario, which is, for example, to reach some goal destination, and there might be more than one crossings nearby, which means that there might be different plans to reach the destination goal. So plan recognition is the stage where the robot should disambiguate these different plans and recognize which one the handler is following. In this case, the immediate instruction that the handler might give to the robot is hop up, which means move on forward. The robot should then perform a consistency check to find out that moving forward as requested will conflict with the safety global objective. At this point, the robot should be certain enough in its understanding of the global and local objectives to decide to override the hop up command. The robot should then use mediation, which might just be stopping and waiting for the environment to change, or leveraging alternative plans and guiding the handler towards a different crossing, knowing that there is an alternative path to the handler's goal location. I will briefly present 3 projects that try to tackle different stages of this disobedience process. First, let's start with goal recognition as reinforcement learning. Goal recognition is a highly useful inference task that is prevalent in most, if not all, of the multi-agent interactions you can think of. Autonomous vehicles recognizing that a car nearby is about to change lanes, a retail assistance robot recognizing when to reach a client and offer help, a surgery robot understanding when the physician's actions might lead to an undesired outcome, in adversarial settings, catching attacks online and intercepting them. And even for music generation, an AI agent should recognize other band members' goals to be a good jamming partner. So plan recognition was proposed as a crucial step for artificial intelligence since around the Dartmouth workshop, and it was formally defined in 1986 by Henry Kotz and James Allen as the challenge to infer the goal of an agent given a recipe database and a set of observations. So if we think about this environment, the candidate goals, the fact that we can move up, right, left, down, this is all part of our database of the environment and what can happen. And once we get a sequence of observations, we can infer something specific about this instance of recognition. For example, in this case, we've observed an agent that is probably trying to reach goal number 2. Traditionally, goal recognition gets as input a set of pre-processed symbols representing observed actions. Using a domain model, which is often represented using planning domain theories or grammars, the recognizer runs a planner or a parser to find out which goal is the most likely. This process means that first, this domain theory needs to be given in advance to the recognizer, and second, that it requires long online inference procedures. In goal recognition's reinforcement learning, we are offering a new paradigm in which the domain theory is replaced with a set of learned policies using reinforcement learning, and we learn this set of policies using Q-learning to begin with, which is something that replaces our hand-coded environment. And in the second phase, the goal recognizer itself is replaced with a simple distance metric that uses to infer which goal is the most likely and is very fast to compute online. So as a running example, you can see here the same example we've seen before. We have a set of candidate goals in the environment and a sequence of observations. The first phase is learning the set of policies for each of the possible goals the agent might be pursuing. So you can see that policy pi for G1 assumes this behavior. And of course, in the initial step, you might step up or you might go right. And that is also potentially an optimal behavior. But for brevity and for the sake of this example, let's assume that there is only one thing that makes sense in this environment. And similarly, we learn a policy for goal number 2 and for goal number 3. Then during the second stage, during inference, we match the observations to the policies that we get, and we see which one is most likely to be the one the agent is pursuing. So in this case, we can infer that the right goal is goal number 2. So I won't go into the details. You're welcome to read about it more in the paper. I'll just tell you briefly about the experiments we conducted. We took 3 main problems from planning domains. We took variations of Grackle, goal recognition as Q-learning, and we trained the policies for each potential goal for 500 training episodes. And we compared that to plan recognition as planning, which is a symbolic plan recognition approach by Ramirez and Geffner. We varied the goal recognition problems with varying levels of observability and noise, and we got 210 different goal recognition problems. You can see here 2 graphs that show our approach compared to Ramirez and Geffner. So on the left, you see F-score, which is the total performance of our algorithms. We took 3 different measurements. Max util, it's the blue one. KL divergence is the red one. And divergence point is the yellow one. And we compare them to the baseline Ramirez and Geffner in green. And you can see that in all 3 domains, basically, except for skgrid, all 3 approaches outperform Ramirez and Geffner with 100% observability. And only divergence point was slightly lower than Ramirez and Geffner. And these results became even more obvious when we had lower observability, when we could only see 10% of the actor's performance in the environment. Then goal recognition's reinforcement learning, the variants we used for that, were able to significantly outperform the state of the art. So basically, we were able to solve a lot of the challenges of traditional goal recognition. Instead of costly domain descriptions, we've learned them using reinforcement learning. Because these are full policies of the environment, they are more robust to noise and can handle lower observability rates as well. And we replaced the online planner and parser runs with simple metric evaluation. So it is a big win. And as a bonus, we don't really need perfect policies to get good performance. If we have a policy for goal A and a policy for goal B, it doesn't have to be that the policy for goal A actually reaches goal A. It only needs to be good enough to be more similar to goal A than to goal B. So when we get an observation sequence, we can distinguish between the different policies. So that's also a bonus fact that we don't really need perfect policies. The learning is useful, but it's not that we need to use the most complex, intense reinforcement learning algorithms to get good performance here. Next, I'm going to talk about the second project I'm interested in, related to consistency check. When I want to understand what the handler of the guide robot needs to do, potentially the robot might interrupt them to ask for clarifications. And I'm interested in when to interrupt for more information. So, if you consider a service robot that is deployed in a hospital during a crisis and can assist the staff by fetching required medicine from a storage room, um, the robot might communicate and ask the physician, which room are you going to, so it can fetch the proper medicine on time. On the other hand, if the robot asks all the time, what do you want me to do now? Where should I go now? It can be cumbersome and might cause unwanted interruptions. So instead, we want to think of a way to reason about when to interrupt someone from the medical team and what information do we want to get from them. I argue that interruptions are a type of mild intelligent disobedience. Basically, it's a way in which the robot can ask questions to the physician, but by doing so, it's not meeting the teammate's expectation for the robot to be non-intrusive. It might even have a cost on trust between the person and the robot. But on the other hand, it can potentially promote shared team goals. So there is a benefit and there is a point to reason about when should a robot interrupt and when might it be useful. So we took this medicine fetching example and we translated it into the physical world to see how interruptions from a robot can affect a human teammate. So we had a participant playing the role of the physician, but instead of going to a patient's room, it needs to reach one of four potential locations in this room that you see on the right. Each location is defined using a set of three different shapes, so the participant will need to understand where to go. They are also given a secondary memorization task to memorize a sequence of 10 words of some category, for example, cities, Chicago, Washington, Austin, Seattle, Denver, and so on. When reaching the final location, the participant needs to write down these words using a pen that the robot will fetch for it. So the robot's role is to understand which location the participant is going and fetch the right pen out of the pen station. There's a different pen per station, so the robot needs to know which pen is the right one, and if it's not sure, it will interrupt the participant who's walking and ask for a clarification. In the setup, the participant has a cognitively challenging task to memorize the sequence, go to the right location, and write down the sequence of words. The interruption by the robot will help the robot to be a better collaborator, but we want to see what will be the cost of the interruption on the person. We wanted to see how different types of querying configurations will affect the person. So we tested three different parameters. In terms of the query content first, we asked three different types of questions. What is your goal station? Are you going to a station with a circle where we ask about one shape out of the three? And are you going to a station circle square plus where we ask about a specific station? We expected that the first type of query will be more welcomed but might have a higher cognitive load than the participant who will need to respond not with yes, no, but with a longer description of the station. We also varied query time, where we wanted to test whether the timing matters at the beginning of the trial or in the middle. And in terms of query distance, we used proxemics principles to test the use of queries in different distances between the robot and the person, in the boundary between the personal and the social zone, within the social zone, and beyond. We combined these parameters into 15 different setups and ran a within subject design with 30 participants who experienced the whole 15 setups with breaks between them. We looked at both objective and subjective metrics of performance. Objective was informed using information retrieval metrics, and subjective were informed from were taken from the PSSUQ system usability questionnaire, where we asked about helpfulness, distraction, and comfort. You can see some of the results on the right here. The top one is for proximity from the person, and the lower one is the query type. And in terms of, these are in terms of the subjective interruptions. People found the interrupting robot to be less helpful and more distracting, especially when it queried the person from afar, from being far away from them. However, there was no significant objective interruptions, which means that the performance on the memorization task was not hindered by the question from the robot. So this outcome implies that the way humans perceive the cost of the interruption is not true to its objective cost, and both the objective and subjective metrics should be acknowledged and measured independently. So this research is part of a wider thrust to reason about the value of interruptions or queries in human-robot collaboration. Among other things, we look at planning useful interruptions for a cooperative agent when its teammates are non-optimal, reasoning about queries of imperfect teachers in a shared control settings, and suggesting a next task in training for human motor skill acquisition, which is a project I'm going to elaborate on next. So the last project I'm going to talk about today focuses on physical human-robot interactions in the context of a teacher robot, which, like a guide robot, has a very high level of agency. In this project, we start by looking at some human motor learning task. For example, the bowling cup or kendama, in which the person needs to learn how to lead the ball into the cup in a fluent swing. There's plenty of research on how long it takes to master a skill like playing kendama, playing tennis, or mastering a piece in a piano, and the magic number that is considered the common rule of thumb for the number of hours you need to invest to master a skill is around 10,000 hours. But in practice, in reality, of course, all models are wrong, and the actual training regime depends more on the quality of training rather than the quantity of training. So we care about whether we can construct an efficient curriculum that will help us master a skill faster. So while we don't know yet the exact mechanism of human learning, several theories have tried to explain what goes on in the background, and many follow a recurring theme. Challenge point theory has been used for motor learning to say that a person learns at a specific point, it has a specific optimal challenge point, which defines the difficulty of the task that will improve their performance the best. And this point in time changes as the person gets better in the task. Scaffolding is a similar concept from education that refers to the support a teacher can provide a student, so it tackles problems that are suitable for learning progression, and with time, the teacher will provide less scaffolding for the person. And lastly, flow channel is very popular in game design, and this theory says that in order for a game or any activity really to be engaging, it is important for that activity to remain within the player's flow channel. So it's not too hard and not too difficult that the person is frustrated. When we compare these theories and others, the common thread is that as the learner gains more expertise, their next best training task will change as well. So we want to sequence this task and form a sort of curriculum that will help them maximize their learning process. So let's quickly look at how we might represent such a problem for a computer. And one of the most common models used for such a problem is Markov decision process, where an agent needs to learn how to act in the environment. And potentially we want to optimize the agent's policy and action selection so it can maximize its reward. So how can we train such an agent? Past work by Narvekar and Stone has investigated the problem of curriculum selection for RL agents using MDPs. So the main goal here is to choose how to sequence tasks for an RL agent so it will reach some threshold performance on a target task faster, which you can see here on the right. So in this model, the teacher is a meta MDP in which each state is the policy of the lower RL agent that needs to learn the target task eventually. And the actions are the potential source tasks that the learner can be trained on. So as this is an MDP, we can use RL techniques to choose the actions for the teacher, which means we can choose the different training tasks and training regime that the teacher introduces to the student. So basically, we are constructing a curriculum. However, it's not straightforward to translate this model from RL agents to human learners. It might be easy to understand the skill state in RL agents because a state is quantifiable, but it's very difficult to know a person's internal states. We also don't know how a mapping how transfer will happen between one task to another. So, for example, if you play tennis and you practice your underhand, will that improve your overhand, or it might somehow conflict with that? And lastly, with an RL agent, we can evaluate its current skill by letting it perform the target task with its learning component shut down. But with people, we don't have such a switch, and we can't turn off learning. Any skill test we perform with people will still be part of the learning curriculum. So given these modeling challenges, we've defined the human skill curriculum arc of decision process, or HCMDP, which acts as a teacher to a human learner. And the main thing here basically is that now we can't see the actual state of the person, which is the gray boxes here. We only have a proxy state, which is influenced by a set of metrics, measurements that we use to quantify how expert a person is in a task. Then we can offer the next task and so on and so forth. And you might notice that like CMDP is a type of an MDP, HCMDP is a type of POMDP. This is what we've been able to do in this project so far. We found intrinsic and extrinsic measures of skill in highly coupled human exoskeleton tasks. We introduced two new platforms for dynamic human motor skill learning, the Reach Ninja that you see here on the right, where you need to capture as many blue markers as possible, and Kendama. And we already have promising results showing that having a robot, an exoskeleton, does not hamper with learning of these tasks. So this is very exciting, and we are now ready to use curriculum learning approaches to better inform the curriculum design for people. So I go back to my original question. Why didn't the robot cross the road? Because it recognized a discrepancy between the global and local objectives of the handler, or an inconsistency between the handler's plan and the objectives. It then went on to consider the proper mediation that will maintain all objectives and will promote trust through legibility and explainability. So I'd like to take a moment to mention a couple of workshops I'm involved in organizing: Theory of Mind in AI and Rebellion and Disobedience in AI. Both are efforts to support the growing and diverse community interested in these types of problems, and I do encourage you to check out these websites and learn more about it. As no man is an island, I would like to mention my collaborators throughout the years. I've had the privilege to work with wonderful scientists, researchers, engineers, and students. And I'll be very happy to have additional names and faces on this slide. So please reach out to me if you have any questions or you want to talk about research. Thank you so much.